In this lesson, we introduce polytopes, which are very important algebraic structures when dealing with systems of linear inequations and play a very important role in linear programming problems. First, we will provide the definition of polytope and some particular examples for you to visualize and have a more intuitive idea of what a polytope is. Next, we will analyze the most important elements associated with this concept, such as vertices, edges, faces, and facets. Finally, we will give the parametric equations of a polytope, which will permit us to generate all vectors in a given polytope. Next, we start with the polytope concept. What is a polytope? A polytope is a set of vectors which is generated by linear convex combinations of a given subset of vectors. If we have a subset of vectors such as A1, A2, An, by means of linear combinations with coefficients adding 1 lambda sub I times A sub I from 1 to n, we get vectors x such that if we change the coefficients lambda in all possible ways, forcing all coefficients to be greater or equal to 0, that is, such that they belong to the R plus set, and adding up to 1, then we have a polytope. To refer to linear convex combinations, we will always use the Greek letter lambda. That is, lambda will represent a subset of non-negative real numbers, such that all of them add up to 1. Thus, we have special linear combinations that are called linear convex combinations. Next, we will see some particular examples of linear convex combinations that will lead to simple polytopes and will allow you to visualize what a polytope is. The first example, the simplest one that you can have, is a unique vector, which can be considered as a linear combination of itself x with a coefficient 1, which is greater than 0 and adds up to 1, because it is a single number. Then we have a single vector which can be associated with a single point in the figure. In the second example, we have a set of vectors which is generated by means of linear convex combinations of two vectors, A1 and A2, that point to the indicated segment extremes, as shown in the figure. Then we have that lambda times A1 plus 1 minus lambda times A2, with lambda between 0 and 1, provides all polytope vectors. Note that since they have to add up to 1, if one is lambda, the other must be 1 minus lambda. Playing with lambda, we can generate all vectors. Making lambda equal to 0 or 1, we obtain the two extremes, A2 and A1 respectively. If we make lambda equal to 0.5, we obtain the middle vector, and if we make lambda equal to 1/4, we obtain the vector located at a distance 1/4 from the left extreme. The third example is the case of a triangle. Since a triangle has three vertices, it is generated by the three vectors that you have there, pointing to the three vertices. Then, combining with linear convex combination those three vectors with coefficients adding to 1, we generate all possible vectors with associated points inside the triangle. Similarly, we have the tetrahedron, which can be obtained with linear convex combinations of the four vertices. Finally, we have the cube. Since the cube has 8 vertices, we can consider vectors whose arrows are at the vertices, and by means of linear convex combinations of these 8 vectors, such that the 8 coefficients, lambda 1, lambda 2 to lambda 8, add up to 1, we can get all vectors inside the cube. This will allow us to understand better what a polytope is. We have mentioned cases of polytopes in linear spaces of dimension 3, in linear spaces of dimension 2 or dimension 1, but we can think of polytopes in linear spaces of any dimension. Next, we provide the parametric equations of a polytope. We use an example. Assume that you have the truncated cube shown in the figure, which is three-dimensional. Since any point inside the polytope can be defined as linear convex combinations of four vertices, we obtain the expression in the transparency that provides all possible points inside the polytope if we select the lambda parameters to be non-negative and adding to 1. We know that in this way we obtain all polytope vectors, or points, and only them. Thus, this equation is the parametric equation of the polytope, and has as parameter the lambda values, one of them redundant, because it can be obtained from the rest of them. It permits us generating all the vectors in the polytope. The equations of a polytope will be derived in another video, but we advance those equations here for the sake of completeness. These equations allow us to check whether or not a vector belongs to the polytope. Next, we analyze the different elements of a polytope. Consider, for example, the tetrahedron shown in the figure, which is a polytope in 3 dimensions. It has 4 vertices, which have dimension 0, 6 edges, the segments joining the vertices, which have dimension 1, they are lengths, and 4 faces, the 2-dimensional triangles, which are surface elements. Even though we have used different names to refer to different dimensional elements, to simplify from now on, we will call them facets of dimensions 2, 1, and 0. We use different names as vertices, edges, and faces for those elements, but thinking in more than 3 dimensions, it is better to call them facets or hyperfaces of dimensions 0, 1, and 2 respectively. We do this because in the case of dimension 20, we have facets of dimensions 19, 18, 17 to 0, and otherwise we will need 20 different names. We will give you an algorithm to obtain the dual cone and the faces of the largest dimension of a cone, and also for the case of polytopes. In this way, even though we cannot see in more than 3 dimensions, we will be able to identify these elements in any dimension, thanks to mathematics, which will allow us to behave as a superband. To clarify further and make more intuitive this process, we use the truncated tube example. If you look to it, you recognize these 3 types of boundary elements. The first are the vertices, which are 10 vertices. They are very important because they allow us to generate all the vectors in the polytope. In fact, they provide a minimal representation of the polytope, because none of them can be removed from the generator set. The second type of elements are the edges of dimension 1, which are those given in the list. You should recognize them in the figure. The third type of elements are the faces of dimension 2, which are those given in the list. You should identify them in the figure. We know that once we have the facets of the maximum dimension, the lower dimensional ones can be obtained by intersections, as it can be done in our example. In this case, it is not complicated to obtain these elements because we are in 3 dimensions, but we can extend these concepts to n dimensions, and then things complicate a lot. All these elements can be obtained by using the dual cone algorithm, which has been implemented as a web page in JavaScript that you can access by using the following link. In addition, the following link shows a video explaining how to use the program. This algorithm provides tables that give the dual cone of a given cone, and it also gives the facets of maximum dimension of the cones. Before ending this lesson, we mentioned that polytopes are very frequent sets arising a solution of system of inequations, because in most cases the feasible set is bounded, and then only polytopes are possible. We advance that in other videos we will see how to identify all the elements of a polytope in any dimension, and how to obtain the equations of a polytope given its parametric equations and vice versa. With this, we end this lesson, and we invite you to see the next video dedicated to the dual cone, which is the basic element to be used in future videos and has a lot of practical applications.